Okay, so in the last section we talked about congruent polygons, and the way we were finding polygons as congruent is to find all of the matching parts congruent. So that's all of the angles and all of the sides. And that works great. Except it takes a while because sometimes there can be a lot of sides and angles. It would be great if there were some shortcuts so that we didn't have to find all of the sides and all of the angles. And hey, there are some shortcuts. In certain instances, triangles can be proved congruent even when we don't know about all of the parts, okay? And so these shortcuts are all going they're all for triangles. This is only going to work for triangles. It wouldn't work for quadrilaterals or pentagons or any other polygons. But these do work for triangles, okay? So let me explain how the first one works. I'm going to zoom out a little bit. Oops. Wrong way. There we go. So I've got these three writing utensils, which are supposed to represent line segments, okay? And they're all different lengths a little bit. And let's say I make a triangle out of these three line segments. Okay, so there's my triangle. Okay, remember that triangle. Let's burn the image of that triangle in our minds. And then I'm going to take these three line segments. I'm going to shuffle them, dump them out on the table, and I'm going to make another triangle. And this triangle will be congruent to the first triangle because there's really only one way that I can make those angles work with those three line segments, okay? Now I don't have the other triangle there anymore, but if you measured the sides, they'd all be the same for sure, right? Because it's the three same line segments, but you'd also find that the angles are going to be the same, okay? And what that means is that if you know all three sides in any two triangles are congruent, then the whole triangles are going to be congruent. And that leads us to our first shortcut, which is called the side-side-side triangle congruence theorem. Okay, that's a lot to, it's a mouthful, and it's a lot to write down. So usually it'll be abbreviated like this. It's the SSS congruency theorem, triangle congruency theorem. And so if I say that those three segments all have corresponding segments over here, then even though I don't know about the angles are going to work out the same, so that means the entire triangles are congruent. Okay. All right, so let's move on to the next one. So now we've got the side-angle-side triangle congruence theorem, okay? And this is really important, SAS for short. It's really important where the angle is in the name of this, okay? This is the included angle. Okay, so that means if I mark any two sides here, let's say it doesn't matter what two you mark, but the included angle is the one that's going to be in between those two particular line segments. So the angle that these two orange line segments form. So the included angle would have to be right here, right? This would be a non-included angle. It's not between the two sides that are marked. That's non-included. But this one is included between the two marked angles, okay? And if I have those same pieces, so in a second triangle, if I've got two matching corresponding congruent sides, and then again, if you've got an included congruent angle, then you can jump to the conclusion that both triangles are congruent, okay? So one way to think about this, let's say I'm just using, I'll zoom out again a little bit. Oops, I always go the wrong way. Okay, so let's say this is a line segment and this is a line segment. Okay, and I'm going to keep them at that angle. And if I wanted to form a triangle out of these pieces, I could close that off like that, right? And then if I kept those same two sides, it would close off in the same way if I have them at the same angle from each other. So that's why any two triangles with that side angle side relationship are going to be congruent to each other. Okay? All right. So it is really important, SAS, right? The A is in between the two S's because that angle is included between the two sides. That's what that means, okay? So on this next one is ASA. And so the S is going to represent the included side. Okay, so this time we're going to have two angles. Pick any two angles you want. It doesn't matter. So let's see. I'll go with this one and this one this time. Okay, and they're going to have matching parts. And I'll have that one match up with that one. And then when I want the included side, I have to think of the side that is part of both of those angles. Okay, so it's the side that's between those two angles, like so. Okay, and then this would be the included side over here. And so this is my ASA situation, angle, side, angle. And again, those triangles are congruent. Okay. All right. So this next one is interesting because it's very, very similar to ASA. It's AAS. The only difference is the placement of the S, right? I still have two angles and a side, but this is going to be a non-included side. Okay, so again, I'll pick the same two angles that I did in the last example. If I have these marked, I need a non-included side now marked. So I can't use the one that I had orange in the last picture. I can't. This is the included side right here and here, right? So it has to be either this one or it could have been the bottom ones. And this will work as well. And if you think about it, if you have two of the angles, really those third angles are going to be congruent by the triangle third angle theorem, which would give you ASA if you wanted to say that those two are congruent, right? So these are really flip sides of the same coin. So ASA always works, but also AAS. And, you know, some people will write this as SAA sometimes, but it's just not written that way in any geometry book. So let's write it AAS, okay? Even though SAA, I suppose, would mean the same thing, okay? All right, so got a bunch of different combinations of A's and S's. So, you know, SSS works. So sometimes people ask, well, what about AAA? Well, let's take a look at that. Now, AAA would actually be the same as just the double angle. So maybe I'll say, maybe I should have written this. But it's just if you have two angles, then you have the third one. Okay. So do I have congruent triangles here? Well, both of these triangles have they're equiangular. All three of the angles are congruent. So, you know, I know all of the angles match up in both triangles, but clearly they're not congruent, right? Because got a small equiangular triangle and a large one. So they have to be the same size and shape. They're the same shape, but not the same size. So these are not going to be congruent to each other. And that's why these do not work. So my answer here is no. Okay? So I see people use that sometimes because it's SSS works, so sometimes people assume that AAA is work. And then is going to work. And then this is the other one. AS and AS backwards. Well, those would be inappropriate. So just right off the bat, I'm going to say no. Okay, those don't work. Not appropriate for school. So that's an easy way to remember that those don't work. But let's talk about why they don't work. Okay, so here I've got an angle and two sides. And my angle is a non-included side, right? So I can see the A is not in between the two S's on these. So this is my ASS or SSA situation. Okay, now let's imagine that there's a little hinge up here at the top. Okay. And what if I took this side and swung it until it was something like this? Okay, and I just eyeballed that, but I could put a line segment that's the same length as this one over here. Okay, and then if I draw these triangles separately, so one of my triangles is going to be the original big triangle. Okay, and that will be represented right here by triangle ABC. Okay, and then I've got this smaller triangle, the one on the left, which is over here. Okay, so if you look at these two triangles, hey, we've got an a set of angles that's congruent, a set of sides that's congruent, another set of sides that's congruent. Okay, and it's a non-included angle, but clearly looking at those, just looking at them, I can tell, no, Those are not congruent, right? This one's way smaller. They're not the same size or shape, so they're definitely not congruent, okay? All right, so let's do a little recap of the theorems that do work and the ones that don't. So this is just what we had on the first page. We had SSS works. We had SAS. Okay, I'm putting the congruent symbol because there are similarity theorems later on that are similar but different. So I do want to indicate that these are congruency theorems. You could write out congruency theorem if you want, but I'm okay with you just putting a congruent symbol. Okay, so these are the 4 that we had that don't work, or that do work, sorry. And then the 2 ones that I see a lot that do not work are these. Okay. All right. So, moving on. Okay, in each pair of triangles, can you conclude that any sides or angles are congruent? Okay, so looking at this first set of triangles, there's part of this that those 2 triangles share, right? So I can say, yeah, well, segment DB is in both triangles. So I'm going to mark that like that. It's congruent to itself. So my answer here is yes. And that's going to be, you can call it BD or DB, it doesn't matter. This is congruent to itself by the reflexive property of congruence. Okay, and that's my explanation right there. I'm just saying what theorem I'm using, okay? So I'm trying to show you some very common scenarios here where you need to find either some sides or angles that aren't marked, okay? And next I've got my bow tie situation. Looks like a bow tie or an hourglass on its side, right? And the what we have here, this angle and this angle are going to be congruent because they're vertical angles. I've got 2 intersecting lines and they're across from each other, right? So those 2 angles are congruent by the vertical angle theorem. So my answer here again is yes. And I'm going to say, I'm not just going to call that angle B, because angle B could be there or there. So I'll call this one ABD. And this one can be CBE. And that's the vertical angles theorem. Okay. All right. So, yeah, on this next one, we got the vertical angles again because it's another bow tie. Okay, so yeah, same reason. I'm not going to put that reason down. But let's look for something else. Okay, so we've got the bow tie situation again. The main difference in this, this diagram from the last one is we've got these little arrows, which means we have some parallel lines. Okay, so pretty much anytime I see parallel lines, I'm thinking, oh, I can maybe use those as my tracks, and maybe I have a transversal that I can use. Okay, so if these are my tracks, and I got 2 different transversals to choose from, so let me start with this one. If I start with that one, now I'm looking for a pair of angles that's part of both triangles, and I could use those 2, right? So I'm thinking, okay, if these tracks are parallel, then that means these are going to be congruent because they're alternate, they're on different sides of the transversal, and they're on the interior, inside of the track, so they're alternate interior angles. So I can just call that angle D and angle C. Those are alternate interior angles, okay? And in the same kind of way, if this was my transversal right here, then I could say, oh, you know what? I really should have put 2 dashes here to show that's a different pair. That's not necessarily congruent to those. But these ones are also going to be alternate interiors. So I can also say angle A is congruent to angle E by the alternate interior angles theorem. I can abbreviate here. Alternate interior angles theorem. Okay. I could have actually got the blue ones by the third angle theorem as well, because I had two pairs of congruent angles already. So then you can get the third one. Okay. All right. So just a little training there on some hidden sides and angles that you may encounter. So now let's move on to the main event, which is figuring out if pairs of triangles are congruent or not, and then identifying how you figure that out. Okay, so are these congruent? If so, identify the theorems used. So I'm thinking about that list I had, and here I've got two sides and an included angle, two sides and an included angle. So SAS is one of those theorems. So I'm going to say yes, and here's my explanation, or here's my theorem used, right? That's the SAS triangle congruency theorem. Okay, moving on. Here I've got three pairs of sides. This would be SSS, and that again is one of the theorems that works. Okay. If you want to pause the video and try the rest of these out, it's just the same kind of thing from here on out. Okay. This next one, I've got two sides and a non-included angle. Uh-oh, that's not going to work, right? Neither would SSA. S and S backwards do not work. This is going to be a nope. Maybe those triangles are congruent, but I can't tell based on the given info because that's not one of my congruency theorems. Okay. Next up, I have two angles and a non-included side in each pair. So two angles and a non-included side. That is one of my congruency theorems. Okay. Next up, two angles and an included side. This side is in between those two angles. This is going to be yes, ASA. Okay. A lot of times on problems like this, I see people say SAS. I think people just flip it around, but you got to think, what is there two of? What is there one of in each triangle? It's got two angles, right? And an included side. And then this would be AAA. But hang on, that doesn't work, right? Because we could, one of these triangles could be slightly bigger than the other one, and they wouldn't necessarily be congruent then. Okay, like you can have a big equilateral triangle and a small one, and they won't be congruent, but all the angles will be congruent. Okay. Okay, and then we got more of these types of problems on the next two pages. They just, some of them get a little bit more complex, but not too bad. Okay, this next one, you could actually use the vertical angles here, and then you could use SAS, but we don't have to do that, right? We can do it right off the bat because we've got SSS, three sets of sides. This is a yes, right? Okay. Whoops, I'm guessing I meant to do SAS here because I put two SSS's in a row. Oh well. Okay. All right. Next up, I'm looking at this. We've got an angle. We've got a side. It's not enough, right? Just one angle and one side's not enough. So then I'm thinking, is there anything else I can find? And there is here because I've got those two intersecting lines, which allows me to say, hey, those two angles are congruent. Now I've got an angle, and a non-included side. That's going to work by AAS then. Okay. Same kind of deal here. Again, we've got, you'll see these same kind of patterns over and over again. So two S's is not enough, right? SSS works, not just SS. So we need something else. And again, we've got intersecting lines, which allows us to get those angles. Now I'm looking at this triangle, got two sides, that's an included angle. So this is going to be yes by SAS. Okay. All right, next up. All right, now this doesn't say that those two right angles are congruent, but they are, right? All right angles are congruent. So if you want to get technical, you could say, well, you use the right angles congruence theorem to say that those are congruent, and now you have SAS, right? So I'm going to say yes, and then I'm going to say I use the right angles congruence theorem. and SAS. If you just said SAS, it wouldn't make me that sad. That's not a terrible crime, because it's pretty obvious that those are congruent. But, you know, technically, we use that congruence theorem there, okay? And then moving on to the next one, we've only got one piece, just an S so far, okay? So I want to think, well, what else can I do? I can do a number of things. I can get vertical angles right here, okay? And then I could also, since I've got those parallel lines, that's making me think, well, can I do something with the transversal and tracks? And I can do alternate interior angles like so. And you could actually do alternate interior angles again using the other transversal. Okay, you can only do that if you've got the parallel tracks. If you don't have the parallel tracks, that doesn't work. Okay, and now I actually have some different options. I could do AAS or I could do ASA. Okay, so either of those would work. And you know, you didn't really have to do the vertical angles because you could have just done these and then you have enough for ASA. So you can do a number of things here. I'll say, well, let me just say that AAS or, and you certainly wouldn't need both of these, but those both work, okay, depending on which pieces you decided to get or which ones you got first. And, you know, you'd want to use vertical angles here is optional if you want the ones I have purple. You definitely have to use alternate interior angles theorem. Because you're going to need at least one of these sets, right? And the only way to get at least your first one is to use alternate interior angles theorem. This is a yes, right? Okay, and then let's move on to the last page. Okay, same question. I'm looking at this, I got an angle and a side. Oh, got my bow tie thing again, so vertical angles again gives me these two. Vertical angles theorem. And then ASA. So, you know, for my explanation, I'm also saying what theorems I use to get the different pieces if I need different sides or angles. Okay, I'm not just saying the congruency theorem. Okay, next up, again, right off the bat, I'm thinking, oh, got the intersecting lines. And then looking at, hey, I've got two angles here and a side, but it's the non-included side, right? The included side would be right here. This is non-included, so this is going to be AAS. So I use vertical angles theorem again. And then AAS. Okay. All right, next up. Well, in this particular problem, we've got a side that is part of both triangles. So that means I can say that this is congruent to itself by the reflexive property of congruence. Okay, and then I'm thinking, oh, I've got two sets of sides and an included angle. So used reflexive. And then SAS. Okay. Very similar on the next problem. I've got this included side again. And I can say that side is congruent to itself. And now I've got three sets of sides, three pairs of sides. So this would be SSS. So I'm using reflexive property of congruence and then SSS, triangle congruence theorem. Okay. All right. All right. Two sets of angles. That's nice, but it's not enough. Yet again, got this shared side. Okay, now I'm thinking, does this work? I've got AAS. Yeah, AAS does work. Okay, and the last one. Shared side again. Okay, the more of these you do, the more repetitive they get, and you'll a lot of times you'll just look at these and see right away, oh, you're going to use reflexive property or you're going to use vertical angles theorem. Those are the ones that come up the most often. Occasionally you might use alternate interior angles or something like that, but usually it's either vertical angles or when you have the intersecting lines, or reflexive when we've got the shared line. This was ASA, yeah, two sides and two angles and an included side, right? It's the included side there. Okay, and that is it. See you next time.